All right, welcome back. You know, every programmer has a sort of mental toolbox they reach for, right? But here's the question. Are you always using the right tool for the job? Today, we're going to stock your C++ toolbox with the absolute best data structures out there. The goal? To take your code from just, well, working, to being truly efficient. Code that really flies.
So what is the secret? What separates code that just gets the job done from code that is seriously high performance? You know, it's not always about memorizing some super complex algorithm. Not at first, anyway. It's actually about something way more fundamental, choosing the right way to store your data. So let's crack open that toolbox and grab the first, most essential tool we've got.
Okay, first up, the absolute workhorse of our toolbox. This is the one you're going to reach for 90% of the time. Think of it like the hammer in your toolkit, the mighty C++ vector.
So what is a vector really? Well, at its core, it's just a dynamic array. And what that means is, unlike those old-school C-style arrays where you had to know the exact size up front, a vector can grow and shrink on the fly. You need more space? It handles it. Need less? It can do that too. That's exactly why it's the go-to, the default choice, whenever you just need a flexible list of things.
And here's why it's so popular. Look at these performance numbers. Accessing an element by its index, v sub 5 or v sub 100, is basically instantaneous. That's what O of 1, or constant time, means. It doesn't matter if the vector has 10 elements or a million, the time to get to it is the same. Same goes for adding or removing from the very end. Now you might see that little on average next to pushback. What's that about? Well, sometimes when you add an element, the vector runs out of room, so it has to go find a bigger chunk of memory and copy everything over. But, and this is the clever part, it does this so efficiently that over thousands of additions, the average cost is still considered O of 1. Super smart.
And honestly, using one couldn't be easier. You just declare it, and then you start using pushback to add elements to the end. That's it. The vector takes care of all the messy memory management stuff behind the scenes for you. It's just clean, simple, and incredibly efficient.
Okay, so the vector is fantastic for keeping things in a list. But what if your problem is different? What if you don't care about the order so much, but you need to do two things really, really well? Quickly check if something exists in a giant collection, and make absolutely sure you have no duplicates. For that job, we need to pull a more specialized tool out of our toolbox, the set.
A set does pretty much exactly what it sounds like. It holds a collection of items, but with one big rule. Every item has to be unique. So if you try to add the number 5 to a set 3 times, guess what? It's only in there once. Its entire reason for existing is to answer one question and answer it incredibly fast. Hey, is this item in the collection? Yes or no?
Now, this is where it gets interesting, because you actually have two flavors of sets. This is a really fundamental trade-off you're going to see again and again. On the left, you have the standard set. Under the hood, it's using something called a balanced binary tree, which is just a fancy way of saying it keeps all your stuff sorted all the time. The lookup speed is O of log n. A great analogy is looking up a word in a dictionary. You don't scan every page, you use the alphabetical order to jump right to the section you need. It's super fast, but it's not instant. Now on the right, you have the unordered set. This thing uses a totally different technique called hashing. The best way to think about this is like a magical filing cabinet. You give it an item, and it instantly knows which drawer to put it in or look for it in. The speed is O of 1. That's constant time. It's basically instant. But here's the catch. The drawers are in no particular order. It's a total mess inside. So the choice is all yours. Do you need your stuff to stay sorted, or do you just need the absolute fastest possible lookup speed?
Okay, time for a classic interview question, a real gotcha that you might see on an exam. There's a version of set called a multiset, and it does allow duplicates. So let's say you have a multiset with 3 5s in it. If you call s.erase5, it doesn't just remove one, it removes all of them. Poof, they're gone. So how do you get rid of just a single one? Well, the trick is that you can't tell erase the value you want to remove. You have to give it the location of the one you want to remove. You do this by first calling s.55. That gives you what's called an iterator. Think of it like a pointer to the very first 5 it finds. Then you pass that iterator to erase, and it will only remove that one specific element. It's a subtle point, but a really important one to know.
All right, let's grab our next tool. This one is all about labeling your data. It's for when you need to connect one piece of information to another. You know, like looking up a word to find its definition, or looking up a name to find a phone number. For this, we need a map.
So, a map is basically a collection of key-value pairs. You can think of it like a super-powered array. You know how a normal array only lets you use numbers as indices, 0, 1, 2, and so on? Well, a map lets you use almost anything as the index, which we call a key. The key could be a string, like someone's name, it could be a number, like a user ID, and each of those unique keys points to a specific value. It's an incredibly powerful way to associate data.
And hey, does this look familiar? It should. Just like with sets, we have the exact same fundamental trade-off with maps. You've got the standard map, which keeps its keys sorted for you. It's that O of log n dictionary model again. And then you've got the unordered map, which uses hashing to give you that blazing fast O of 1 magical filing cabinet lookup speed. And just like before, the trade-off is order. With unordered map, your keys are all jumbled up. So once again, the choice is yours. Do you need your keys to be sorted, or do you need the absolute maximum lookup speed?
Okay, everyone, lean in for this one, because this is probably one of the biggest and most common traps in all of C++. If you use the square brackets to access a key in a map, and that key doesn't actually exist, it doesn't give you an error, no. What it does is it creates that key on the spot and assigns it a default value, like 0 if your values are integers. This can lead to some really nasty, hard-to-find bugs, because you think you're just reading data, but you're actually writing it. The safe, correct way to check if a key exists is to use the .count method. Please remember that one.
All right, we've covered the big three: vector, set, and map. Now let's do a quick lightning round of some more specialized tools. These are things you won't use every single day, but when you need them, they are the perfect tool for the job.
First up is the DQ, which is short for double-ended queue, and it's usually pronounced DEC. Think of this as a vector on steroids. It does everything a vector can do, but it adds one killer feature. It can also add and remove elements from the front in fast O1 time. This makes it perfect for something like a sliding window algorithm, where you're constantly adding a new element to one side and dropping an old one off the other.
Next up, the stack. The concept here is super simple: last in, first out, or LIFO, as you'll often hear. The best analogy is a stack of plates at a buffet. You add a clean plate to the top, and you take a plate from the top. The last one that was put on is the first one you take off. This simple idea powers so many things, like the undo feature in your text editor or the back button in your web browser.
And if a stack is a pile of plates, a queue is a line at the checkout counter. It's the exact opposite principle: first in, first out, or FIFO. The first person who gets in line is the first person to get served. This is all about fairness, and it's essential for things like managing incoming requests on a web server or handling jobs in a print queue. First come, first served.
Last in our lightning round is the priority queue. Now don't let the name fool you. This is nothing like a regular queue. It's not about first in, first out. Here, the only thing that matters is most important out. Every item you put in has a value or a priority, and the priority queue magically rearranges itself so that the highest priority item, which by default is the largest element, is always sitting right at the top, ready for you to grab in O of 1 time. It's incredibly efficient, usually implemented with a data structure called a heap.
Okay, our toolbox is officially stocked. Now it's time for the masterclass. Let's put this all together and see how choosing the right tool makes a massive difference in a real-world problem. Here's the scenario. You're given two huge lists of numbers, and your job is to figure out how many numbers appear in both lists. So here's our first attempt, algorithm 1. The logic is pretty straightforward. We'll take the first list of numbers and just dump them all into a standard set. This automatically handles duplicates for us. Then we just walk through the second list one number at a time, and for each one, we ask the set, hey, have you seen this number before? Since each check in a set takes O of log n time, and we do this n times, our total complexity is O of n log n. Now, based on what we just learned, you're probably thinking, wait, why not use an unordered set? And you're right, that will be our algorithm 2, and it should be a lot faster. Let's keep that in mind and look at another approach first.
All right, now let's look at a completely different way to solve this, algorithm 3. With this one, we're not going to use any fancy data structures at all. No sets, no maps. We're just going to take both of our lists and sort them. Once they're both sorted, we can do this clever trick where we use 2 pointers, one for each list, and just walk through them both at the same time to find the matches. The most expensive part of this whole process is the sorting, which is typically O(n) log n. So on paper, algorithm 1 with the set and this sorting approach have the exact same time complexity. They should be about the same speed, right?
Well, let's look at the actual numbers. The results might surprise you. Just as we expected, algorithm 1, using the standard set, is the slowest. And, sure enough, switching to an unordered set for algorithm 2 gives us a huge speed up,
about 5 times faster. That makes sense. But then, look at algorithm 3, the simple sorting approach. It's not just a little bit faster than the unordered set, it's almost twice as fast again. At 5 million numbers, the dumb sorting algorithm is more than 10 times faster than our original set approach. How is that possible? They have the same big O complexity.
So what gives? Why the massive difference? This right here is probably the single most important lesson today. Big O notation is great. It tells you how an algorithm's performance scales as the input gets bigger, but it hides a really important detail, the constant factor, the actual cost of each operation. Sorting a vector is like an incredibly efficient factory assembly line. All the data is laid out neatly in a row in memory, and the CPU can just blaze through it. Building a set or an unordered set, on the other hand, involves a lot more overhead. It's more like carefully placing items all over a warehouse. There's a lot of jumping around in memory, allocating little bits of space here and there, and that jumping around is slow. The simple, memory-friendly assembly line just absolutely destroyed the more complex approach. It's a powerful reminder. Never, ever underestimate how much speed you can get from keeping your data packed together tightly in memory.
So, let's wrap this up with a quick cheat sheet for your toolbox. If you need a simple dynamic list, Vector is your absolute go-to. 99% of the time, that's what you want. If you need to check if things exist or keep a unique collection, your default should always be unordered set for maximum speed. Only use a set if you absolutely must have them sorted. Same story for key-value pairs. Start with unordered map for that sweet O of 1 speed, and only fall back to map if you need the keys in order. And finally, the big lesson from our masterclass. Never forget that sometimes the simplest tool in the box, just a plain old sort, can be the fastest one of all.
There you have it. Your C++ toolbox is now officially upgraded. You don't just have the tools, you have the knowledge to choose the right one, so you can solve problems not just correctly, but elegantly and efficiently. The only question left is, what are you going to build? Thanks for joining me.